Welcome! Today, we'll dive into the problem number 406, queue reconstruction by height. This is a fascinating problem that challenges us to manipulate and reorder data based on specific constraints. If you're ready, let's break it down step by step. In this problem, we are tasked with reconstructing a queue of people based on two parameters, their height and a value that specifies how many people taller or equal in height stand in front of them. Each person is represented as a pair of integers, where the first value, h, is the person's height, and the second value, k, is the number of people in front of this person who are at least as tall as they are. The goal is to return the queue as a list of such pairs, arranged in the correct order that satisfies these conditions. The input is a two-dimensional list of integers, where each sublist represents one person, and the output is also a two-dimensional list after reconstructing the queue. Let's examine an example to better understand this setup. For the input people equals 7, 0, 4, 4, 7, 1, 5, 0, 6, 1, 5, 2, the reconstructed queue is 5, 0, 7, 0, 5, 2, 6, 1, 4, 4, 7, 1. Each person in the output queue satisfies the given conditions. For example, person 7, 0 is placed at index 0, meaning no one taller or equal in height stands in front of them. Similarly, person 4, 4 is at index 4, and there are exactly 4 people taller or equal to their height in front of them. Continuing this way for all the people in the list, the reconstructed queue ensures that everyone's k value is met. Another input, people equals 6, 0, 5, 0, 4, 0, 7, 0, 6, 2, 5, 2, will produce the output queue 4, 0, 5, 0, 5, 2, 6, 0, 6, 2, 7, 0. Let's now consider the constraints of the problem and explore special cases. The problem has a few important constraints. First, the number of people in the input list is between 1 and 2,000. The height of any person can range from 0 up to 10,000, and each k value is always less than the total number of people in the list. These constraints ensure that the input data is valid and guarantees that the queue can always be reconstructed. Additionally, let's consider edge cases. For example, if there's only one person in the queue, like people equals 5, 0, the output is simply 5, 0, since they automatically satisfy the condition. Another interesting case is when all people have the same height but different k values. When all people have the same height, such as people equals 6, 0, 6, 2, 6, 1, the k values alone determine the order. The output in this case is 6, 0, 6, 1, 6, 2, as each k value is directly reflected in their positions. Another scenario is when all k values are 0, like people equals 5, 0, 7, 0, 6, 0. Here, the people are simply sorted by height in ascending order, resulting in 5, 0, 6, 0, 7, 0. These examples demonstrate how the problem handles different edge cases and helps clarify the rules for constructing the queue in a variety of situations. To tackle this problem, we first considered a brute force approach. The intuition here is straightforward. We try to reconstruct the queue by placing people one by one, ensuring that each person's k value representing the number of taller people in front is satisfied. This involves iterating through the queue for each person, counting positions where fewer than k taller people precede them, until we find the correct spot. While this method is conceptually simple, it's inefficient due to its repeated scanning and insertion steps. With a time complexity of n squared, this approach quickly becomes impractical for larger inputs. To address these inefficiencies, we explored a more optimized solution using a greedy algorithm. The key idea here is to sort people in descending order of height and, for those of the same height, in ascending order of k. This strategy ensures that taller individuals are placed first, which simplifies the placement of shorter people since their k values remain unaffected by taller individuals already in the queue. By leveraging this ordering, we can build the queue in a way that satisfies the k condition without unnecessary recalculations. The process for implementing this greedy algorithm starts with sorting the input list as described, by height in descending order, and by k in ascending order for people of the same height. Next, we initialize an empty queue. Then, for each person in the sorted list, we insert them at the index specified by their k value. This ensures that the condition for k is maintained for each person as they're placed. Looking at the complexity, the sorting step takes O, n asterisk log n, and each insertion operation can take up to O, n, in the worst case. Combining these, the total time complexity is approximately O, n squared, for larger inputs. However, compared to the brute force method, this approach is far more efficient as it avoids redundant recalculations during insertion. The advantages are clear: it's logical, easy to understand, and significantly faster than brute force. Its main limitation, though, is that the insertion step still contributes to an O, n squared, complexity in the worst case. Despite this, it strikes a good balance between simplicity and performance for most scenarios. An alternative strategy involves using a binary index tree, or bit, to optimize the insertion step. The idea here is to use advanced data structures like bit or segment trees to efficiently find the correct position for each person, reducing the insertion time to O, log n. While this approach offers a theoretical advantage, its practical drawbacks include high implementation complexity and the need for specialized knowledge, making it less accessible for many developers. After evaluating these options, the greedy algorithm was chosen as the preferred solution. It offers a balance of simplicity and efficiency, making it ideal for typical interview scenarios or general use. The key insight that makes this approach work is recognizing that placing taller individuals first simplifies the placement of shorter ones, as their K conditions remain unaffected. This realization allows us to efficiently reconstruct the queue while adhering to the problem constraints. Comparing the strategies, the greedy approach outperforms brute force by eliminating redundant calculations and is more practical than bit due to its lower complexity and overhead. In conclusion, the greedy algorithm provides a clear, intuitive, and efficient solution to this problem, making it the best choice overall. This problem focuses on reconstructing a queue based on specific height and positional constraints. Each person is represented as a pair, h, k, where h indicates their height and k specifies the number of people taller or of equal height standing in front of them. The goal is to rearrange these people into a queue such that every person's k condition is satisfied. To solve this, we'll start by sorting the input list. First, we sort the people by their height in descending order. For those with the same height, we sort them by their k value in ascending order. This order ensures that taller individuals are handled first, as they aren't influenced by shorter people who will be placed later. For instance, sorting the input list 7 0 4 4 7 1 5 0 6 1 5 2 results in 7 0 7 1 6 1 5 0 5 2 4 4. Finally, we initialize an empty queue, which will act as the structure to build the reconstructed arrangement step by step. Now that we have the input sorted, the next step is to insert each person into the queue at the position corresponding to their k value. This is done iteratively. For each person in the sorted list, we use the insert operation to place them at the correct index in the queue. This ensures their k condition is satisfied relative to the taller people already placed. For example, starting with an empty queue, we first insert 7 0, giving us 7 0. Then, 7 1 is inserted at index 1, resulting in 7 0 7 1. Next, 6 1 is inserted at index 1, pushing others to the right and producing 7 0 6 1 7 1. We continue this process 4 5 0 5 2, and finally 4 4, ending with the reconstructed queue 5 0 7 0 5 2 6 1 4 4 7 1. This method works because the list is already sorted, and taller individuals are placed first, simplifying the insertion logic for shorter people. Several key insights make this algorithm effective. First, sorting the input by height simplifies the problem. By processing taller individuals first, we avoid complications from shorter people affecting their placement. Second, the insert operation ensures that each person is placed in the correct position immediately, maintaining the k condition without requiring further adjustments. This approach is inherently greedy, as it places each person in the queue in a way that satisfies their constraints incrementally. In terms of data structures, we use a list to store the reconstructed queue. While the insert operation may seem expensive, it's manageable due to the small size of the queue at each step. The algorithm's time complexity comes from two main components: sorting, which takes O, n log n, and the insert operations, which take O, n, for each of the n people, resulting in O, n squared, in the worst case. This combination makes the overall complexity O, n squared, which is acceptable for the problem scope. To ensure the algorithm works in all scenarios, we consider several edge cases. First, if the input list is empty, the output will also be an empty list. Second, if all individuals have the same height, the algorithm will sort them by their k values and insert them accordingly, maintaining the order. Finally, if there is only one person in the input, they are simply placed in the queue as is. For example, given the input list 7 0 4 4 7 1 5 0 6 1 5 2, the algorithm produces the output 5 0 7 0 5 2 6 1 4 4 7 1. This output satisfies the constraints for every individual, demonstrating the algorithm's ability to handle various scenarios and adhere to the problem's requirements. The solution uses a greedy algorithm to reconstruct the queue efficiently. First, the input list is sorted in descending order of height, h, and then in ascending order of k for people with the same height. This ensures that taller people are processed before shorter ones and that their respective k values are correct when inserted. Next, the algorithm iterates through the sorted list and inserts each person at the index specified by their k value into the queue. Because taller people are inserted first, the shorter people's k values remain consistent with the number of taller or equal height people already in the queue. This approach guarantees the correct order while maintaining an efficient runtime of O, n squared, where n is the number of people, due to the insert operation in a list. This implementation is concise, handles edge cases, like an empty list, and ensures the k condition is satisfied for all individuals in the queue. This is the Java implementation of LeetCode problem number 406, queue reconstruction by height. The logic mirrors the Python solution with key differences such as explicit type declarations, use of Java's arrays.sort for sorting, and linked list for inserting elements at specific indices. The solution sorts the input array by height in descending order and by co-value in ascending order. Then, it reconstructs the queue using a list, ensuring that each person is inserted at their specified k-value index. Finally, the list is converted back to an array for the output. In this problem, we are tasked with reconstructing a queue of people based on their heights and a specific constraint. Each person is represented as a pair, h, k, where h is the height of the person, and k is the number of people in front of them who are at least as tall as they are. Our goal is to reorder the list of people to satisfy these k constraints for everyone. The key idea behind solving this problem involves two steps. First, we sort the input list in descending order of height. For people with the same height, we sort them in ascending order of their k value. This ensures that taller people are considered first, and within the same height group, we prioritize those who should have fewer people in front of them. Second, we iteratively insert each person into the queue at the index specified by their k value. By processing taller people first, the k constraint for shorter people will naturally be preserved. For example, if we start with the input 7 0 4 4 7 1 5 0 6 1 5 2, the first step is to sort the input. After sorting, we get 7 0 7 1 6 1 5 0 5 2 4 4. This sorted order sets the foundation for the next step, where we reconstruct the queue by inserting each person at their respective k index. Now that we have the sorted list, we can begin inserting each person into the queue at their k index. Starting with an empty queue, we first insert 7 0 at index 0, resulting in 7 0. Next, we insert 7 1 at index 1, making the queue 7 0 7 1. Then, we insert 6 1 at index 1. This pushes 7 1 to the right, giving us 7 0 6 1 7 1. Continuing, we insert 5 0 at index 0, which shifts all existing elements to the right, resulting in 5 0 7 0 6 1 7 1. Next, 5 2 is inserted at index 2, placing it between 7 0 and 6 1, resulting in 5 0 7 0 5 2 6 1 7 1. Finally, 4 4 is added at index 4, pushing 7 1 1 position further to the right, and we get the final queue 5 0 7 0 5 2 6 1 4 4 7 1. This process ensures that each person is placed in the correct position based on their k value. Now, let's look at another example to reinforce the concept. In the second example, the input is 6, 0, 5, 0, 4, 0, 3, 2, 2, 2, 1, 4. After sorting by height in descending order and k in ascending order, the sorted list is 6, 0, 5, 0, 4, 0, 3, 2, 2, 2, 1, 4. We start inserting people into the queue. First, 6, 0 is placed at index 0, giving us 6, 0. Next, 5, 0 is inserted at index 0, pushing 6, 0 to the right, resulting in 5, 0, 6, 0. Then, 4, 0 is inserted at index 0, shifting the other elements to the right, and the queue becomes 4, 0, 5, 0, 6, 0. Moving on, 3, 2 is added at index 2, placing it between 5, 0 and 6, 0, giving us 4, 0, 5, 0, 3, 2, 6, 0. Next, 2, 2 is inserted at index 2, pushing 3, 2, and 6, 0 further to the right, resulting in 4, 0, 5, 0, 2, 2, 3, 2, 6, 0. Finally, 1, 4 is added at index 4, creating the final queue 4, 0, 5, 0, 2, 2, 3, 2, 1, 4, 6, 0. This step-by-step process ensures that each person is correctly positioned to satisfy their k constraint. For the final example, the input is 9, 0, 7, 0, 1, 9. After sorting, the order becomes 9, 0, 7, 0, 1, 9. We begin inserting people into the queue. First, 9, 0 is placed at index 0, resulting in 9, 0. Next, 7, 0 is added at index 0, pushing 9, 0 to the right, and the queue becomes 7, 0, 9, 0. Finally, 1, 9 is inserted at index 9, which simply appends it to the end of the queue, giving 7, 0, 9, 0, 1, 9. This example highlights how the algorithm handles edge cases, such as a person with a very high k value. By sorting and inserting strategically, we ensure that the final queue satisfies all constraints. To summarize, this algorithm follows a greedy approach. It sorts people by height and inserts them at their k index. This guarantees correctness and avoids unnecessary backtracking, making it an efficient solution to the problem. To analyze the time complexity of our solution, we start by breaking it down into two main steps: sorting the input list and inserting elements into the queue based on their indices. First, consider the sorting step. Here, we use Python's built-in sort function with a custom key. This key sorts the list of people by height in descending order, and for those with the same height, by their k value in ascending order. Sorting a list of size n typically requires n log n time. Since the custom key involves operations like accessing and negating the height or accessing k, which are all constant time operations, it does not add extra complexity. Thus, the sorting step contributes n log n to the overall time complexity of our solution. Next, let's analyze the insertion step. After sorting the list, we iterate through each person and insert them into the queue at the index specified by their k value. In Python, inserting an element into a list at a specific position involves shifting elements to the right, which takes m time, where m is the current size of the list. For the first person inserted, the cost is 0, for the second person 1, and so on, up to n1 for the last person. Adding these up gives a total cost of 0, plus 1, plus 2, plus n1, which simplifies to n squared. When we combine this with the sorting step, the overall time complexity becomes n log n plus n squared. Since n squared dominates, the total time complexity of the solution is n squared. Now, let's examine the space complexity. First, consider the input and output storage requirements. The input list of people is sorted in place, meaning no additional space is required for sorting. However, the queue list, which is used to construct the result, requires space to store all n people, contributing n to the space complexity. Additionally, Python's sorting algorithm, timsort, uses auxiliary space proportional to the size of the input, which is n in the worst case. Since no other significant data structures are used, the total space complexity of this approach is n. To better understand the efficiency of this approach, let's compare it to a brute force solution. In a naive approach, we might simulate the k condition for each person by iterating over the queue to find their correct position. This involves nested loops where each iteration requires scanning the queue to count the number of taller or equal height people. For n people, this would result in a time complexity of n cubed, which is far less efficient than our optimized approach. By contrast, the optimized solution first sorts the list and then uses efficient insertions to achieve a time complexity of n squared. This is a significant improvement, especially for larger input sizes, and highlights the advantage of the optimized approach. Finally, let's consider the best, average, and worst-case scenarios for the optimized approach. Even in the best case, such as when the input list is already sorted, the insertion step still requires n squared operations because elements in the list must be shifted during each insertion. Therefore, the best, average, and worst cases all have the same time complexity of n squared. To mathematically validate this, note that inserting n elements into a list involves costs that grow linearly with the size of the list, resulting in a total of n squared. While the sorting step adds n log n, it is dominated by the n squared insertion step. Overall, this approach provides a substantial improvement over the naive n cubed solution, with a time complexity of n squared and a space complexity of n. When solving the queue reconstruction by height problem, there are some common mistakes to be aware of. First, improper handling of the k-value is a frequent issue. Remember, the k-value represents the number of people already in the queue who are taller than or equal to the current person. Misinterpreting this can lead to invalid queue configurations that violate the problem's constraints. Another mistake is sorting without a proper strategy. Some candidates attempt to sort the input but fail to account for both height and k values together. Sorting by height alone or by k alone ignores the dependency between these attributes, which is critical for solving the problem correctly. Inefficient placement is another pitfall. A brute force approach that repeatedly iterates through the queue for each person leads to excessive complexity, often n cubed, or worse, making it impractical for larger inputs. Finally, many candidates overlook edge cases, such as scenarios where everyone has the same height or all k values are 0. Ignoring these edge cases can result in solutions that fail under specific conditions, leading to incorrect outputs. Another common issue is failing to validate the final result. Some solutions construct the queue but forget to verify if the k condition is satisfied for each person. This can produce outputs that may appear correct at first glance but actually violate the problem's requirements. To avoid these pitfalls, it's crucial to deeply understand the problem statement. During an interview, take the time to clarify constraints and examples, especially the meaning of the k value, as confusion here is a frequent source of errors. Leveraging sorting is a key insight for solving this problem efficiently. A robust approach involves sorting people by height in descending order, using the k value as a tiebreaker when heights are the same, and then inserting them into the queue based on the k value. This ensures correctness while improving efficiency. Additionally, it's essential to communicate the trade-offs of your approach. For example, a solution with n squared complexity for sorting and inserting is typically acceptable given the constraints. Always plan for edge cases, such as empty inputs, all k values being 0, or multiple people sharing identical attributes, and explicitly mention these during your explanation. The concepts in this problem are closely related to other sorting-based problems on LeetCode. For instance, the queue reconstruction by height problem itself is a prime example of using sorting and insertion to meet specific constraints. Another related problem is LeetCode 56, merge intervals. This problem also involves sorting and carefully managing intervals, which requires a similar strategy of handling dependencies between elements. LeetCode 1387, sort integers by the power value, introduces the idea of sorting based on custom criteria, which parallels the sorting logic used here with height and k values. Finally, LeetCode 1365, how many numbers are smaller than the current number, involves counting constraints, which shares conceptual similarities with the k value in this problem. Exploring these related problems can help you build a deeper understanding of sorting and its applications in algorithmic problem solving. There are multiple ways to approach this problem, each with its own trade-offs. One efficient method is sorting and insertion. Here, you first sort people by height in descending order. For those with the same height, sort by their k-value in ascending order. Then, insert each person into the queue at the index specified by their k-value. This approach achieves O, n log n, for sorting and O, n squared, for insertion, making it suitable for moderate input sizes. Another option is using a segment tree or Fenwick tree. These data structures allow you to efficiently find the correct position for each person during insertion, reducing the overall time complexity to O, n log n. However, implementing these structures is more complex, which may not be ideal for an interview unless specifically requested. Lastly, a greedy simulation approach involves iterating through the sorted list and constructing the queue by placing people in positions where their k condition holds. While this method is often easier to understand, its efficiency depends heavily on how insertion is handled, which could lead to higher complexity. Each approach has its strengths, so choose one based on the problem's constraints and the context in which you're solving it. Thank you for watching. In this session, we explored the problem and its brute force solution. We discussed how understanding constraints and sorting can help tackle similar problems. If you found this valuable, don't forget to like, share, and subscribe. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!